Consider two 50-gallon tanks, which are connected by two flow pipes. The tank on the left is tank X, and the one on the right is tank Y. Flow rates through each pipe are given here in gallons per minute and are arranged in such a way so that each tank is maintained at its capacity at all times. Now each tank contains salt solution at a concentration given in pounds per gallon. We'll leave the initial conditions unspecified here. Tank X receives salt solution at a rate of 1 pound per gallon at 1 gallon per minute. Tank Y receives pure water at a rate of 1 gallon per minute. The problem is, what happens to the amount of salt in pounds as time goes on? If each tank is kept thoroughly mixed at all times so that the concentrations stay the same in each tank, how can we use math to solve this problem? Take a moment and see if you can figure it out. With our setup, we're going to transform this physical system into a system of differential equations. On the left we have tank X, on the right tank Y. Concentrations being X out of 50, meaning pounds per gallon, and Y out of 50, pounds per gallon in each tank respectively. So we'll let X and Y be the amounts of salt in each tank given in pounds. And both of these are functions of time, X of t and Y of t. So that makes them a set of parametric equations. Now what we'll do is we'll develop the derivative here, the rate of change of salt with respect to time. So first we have incoming into tank X 1 pound per gallon at 1 gallon per minute. We also have incoming from tank Y at a concentration of Y over 50 at a rate of 3 gallons per minute. And we're going to subtract away from this the amount that is leaving tank X, which would be 4 gallons per minute of concentration X over 50. So we can write this differential equation as x prime equals 1 plus 350y minus 4 over 50th x. And for dy dt, we have 2 gallons per minute at a concentration of X over 50 pounds per gallon entering tank Y, and we have 3 gallons per minute of a concentration of Y over 50 pounds per gallon leaving the tank, giving us the differential equation y prime equals 2 over 50x minus 3 over 50y. So now we have a system of differential equations. By rearranging a few terms in each equation, we can rewrite it in the following way. X prime plus 4/50ths x minus 3/50th y equals 1, and y prime plus 3/50th y minus 2/50th x equals 0. And the reason that we want to do this is because we want to employ something called a linear operator, a differential linear operator. So we're going to let that linear operator be given by the capital D, so that when we factor this in terms of this linear operator, we get the following equations to read just like this, where capital D again stands for the linear differential operator d by dt. Now, given any system of equations, we can try some of the methods that we're familiar with, like the elimination method, to solve such a system of equations. So let's consider our differential equations written out like this. Alright, and to solve this, we'll use the elimination method by trying to eliminate the x term. So we'll multiply the top by 250 and the bottom by d plus 4 over 50. When we do so, we get these two equations, which will add together And the result will eliminate the x term, giving us something completely in terms of y. Now, cleaning up the differential operator term, we get a quadratic here, which we can factor. And so this now becomes our equation that we must deal with. And we start by a substitution, letting u equal d plus 6 over 50 times y, and then substituting that into the equation above, giving us u prime plus 1 over 50u equals 2 over 50. A first-order differential equation. So let's take a detour and consider how to solve a first-order differential equation. So consider y prime plus p of xy equals some function q of x. The first step in solving such an equation would be to solve the homogeneous equation. By letting q of x equal to 0, we get the homogeneous equation, y prime plus p of xy equals 0. And solving this, which is a separable equation, we get the homogeneous solution to be a constant a times e raised to the negative integral of px dx. Now, the factor that's in there, e raised to the integral of p of x dx, that's known as an integrating factor. And it's going to become very useful in solving the equation that is a non-homogeneous equation. So we're going to multiply both sides of our differential equation by this integrating factor. So y prime plus p of x times y multiplied by the integrating factor, and then q of x multiplied by the integrating factor. The left-hand side, if you expand it out, you'll recognize that it's really the product rule when differentiating y times the integrating factor. So thereby, by setting up this equation in this form, we can then integrate both sides. And by integrating both sides, we can then develop a solution, a general solution. We'll have to compute an integral on the right-hand side, but on the left-hand side, we can get rid of that factor of e to the px dx integral by just multiplying both sides by its inverse. And we get the general solution to look like this. So now, if we were to consider, say, a second-order differential equation, one such as y double prime plus some constant y prime plus a different constant times y equals 0. We'll start off with something homogeneous. And that is with constant coefficients in this case. One might try to take this and factor out a differential operator expression. And with this d squared plus p times d plus q equals 0, this equation is known as the characteristic equation, or sometimes known as the auxiliary equation. It determines the roots, and it gives us three cases of solution. One with real and distinct roots, one with real and repeated roots, or one with complex conjugate roots. The characteristic equation and its roots allow us to develop the general solution to the differential equation. So let's consider each case. First, let's consider two different distinct roots, real roots. And just as we saw before, we're going to make a change of variables. But first we're going to see, just like a quadratic equation, you would solve by setting each factor equal to 0. So we consider that this would have two different solutions of the form a constant times e to a power a to x for the first one and a power bx for the second one. And the general solution would be given by the superposition principle or linearity principle by adding those two particular solutions together, giving us a general solution. The constants c1 and c2 would be, well, they would be determined by an initial condition given on the differential equation. Now, if we consider case 3, which would be the complex conjugate case, this would be two different roots, similar to case 1, but in the complex plane. And for this case, we would treat the roots just in a similar way that we treated case 1, only with complex values. Now, case 2 is when we have a repeated real root. So let's let that root be a, and it would factor in such a way where we would get at least one solution to be able to form a constant times e to the ax power. Then we would make a substitution by letting u equal d minus a times y, rewrite the differential equation, and get a second solution, which is in the form of u is equal to a constant times e to the ax. So the general form of the equation would be something of the form of a sum, but here we get the general solution when we use our integral formulation from before. The general solution works out to be a linear term times e to the ax power. So that's just a general overview about how to treat a second order differential equation with constant coefficients, and that is also a homogeneous equation. Now onto the good stuff. What if this was not a homogeneous equation but equal to some function f of x? The general solution comes from some successive integration, and it comes from also the superposition of the homogeneous solution, which is the solution when f of x is equal to 0, and a particular solution, which would be any known solution. Now, many times it's easy to perhaps guess a particular solution, but not always. And in the case that you cannot guess it, successive integration is the method that we use to develop the particular solution as well as the general solution. And that's the approach I'm going to take here. Alright, so we're going to get our general solution, and first we're going to consider the, of course, characteristic equation that comes from this. We'll make a substitution for letting d minus b times y equal u. Rewrite our differential equation as u prime minus au equals f of x. Plug that into our formula from the integration before, so we get u is equal to this form, using the root of a, and then by substituting it back into the original differential equation, we can then develop the general form of the solution for y using the solution for u. So here you'll see me use q bar as a replacement for that entire expression which we used for u. And so there's two integrals, successive integration that's taking place there, giving us a general solution for y. Now, for our particular physical situation, we have a differential equation which boils down to two different roots, and so we're going to treat it in just the same way we did with the second order differential equation we just looked at. F of x here would be, in the case, 2 over 50. So we get a general solution for u. And you'll see me here writing out the integral explicitly. Integrating that, we actually can simplify this and boil the function down to 2 plus some constant times e to the negative t over 50 power. That would be taking place of the q bar that we were just talking about. And that is going to be in a new integral, the one that we use to solve for y. So now, back substituting the u value in that we just found, we get this differential equation for y, and the solution again by integration becomes e to the negative 6t over 50 times the integral of what we just found times e to the 6t over 50 power dt plus a new constant times e to the negative 6t over 50, that integrating factor. And so at the end of the day, our general solution looks something like this. 10c1 e to the negative t over 50 plus c2 e to the negative 6t over 50 plus 50 thirds. That's our general solution for our amount of salt in tank Y. And it is a function of time. Now what we do with this is we just simply substitute this into our system of equations, just like you would when you find a solution for a regular system of equations. We take this solution and back substitute it into, we'll take this equation here and we'll back substitute our solution into that. So you take y, you differentiate it with respect to time, so you get a y prime, and then we substitute everything into the equation, and what we're left with is x is equal to 50 over 2 times the quantity y prime plus 350 over y, and that works out to be 10c1 e to the negative t over 50 minus 3 halves c2 e to the negative 6t over 50 plus 50 over 2, which is really 25. So now to answer the question, what happens to these quantities of salt as time goes on? Well, as time goes on means we want to take the limit as time goes to infinity. And for the first tank, we get 50 over 2. In the second tank, we get 50 over 3. And for the concentrations, well, in tank 1, it's x over 50, so if we plug that value in, and y over 50 for tank Y and plug its value in, we get the concentration of salt in tank X to be half, and in tank Y to be a third. So now, we've used calculus and differential equations to model a physical situation. And how would we calculate or determine C1 and C2? Well, the answer to that would be if we were given some initial conditions on the system. But that's for another time. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one.